Hi everyone, I am DEBAJYOTI, a faculty of DPL, Delight Physics Lab as you all know, and we have arranged this online lecture series during this quarantine period so that you can access our lectures right from your home. Well, it's quite boring actually, even for us, and this is the most fun that we can have. I guess it won't be that boring. Don't worry, even if you have already done this practical, I can guarantee you that after this entire video, after you have watched this entire video, you will have learned something new today, and I can really assure you that. So please bear with me. One thing is that perhaps my video is coming after a video of a few other faculties, and you might have noticed that everyone is using their own methods, because that's obvious. We all are at home and we don't have this methods to record videos, and so we all are using different ways to convey to you our lectures. I have chosen this slide presentation way, and to be honest, if somebody came up to me and said, okay, you're at home, please watch a video on slides, I myself would not have, because it's not really interactive and I really don't recommend that. But honestly speaking, I've tried to make this as much interactive as possible, and I hope you will like this, not because of its animation or its interactiveness, or I guess you'll like this because of the information that you will get that usually I don't give during the lectures that I give in the classes, because I don't have that much time to explain the theory. So I guess you'll like this. So let's start without much ado. My lecture today is on Carey-Foster bridge. Well, if you have already done this practical, or even if you haven't, don't worry, it's really a very simple practical. Let's see the aim of this practical. Okay, let's read this. To measure the resistance per unit length of the wire of a meter bridge and to determine an unknown fixed resistance by Carey-Foster method. So from this aim, as you can see, it's two-part. Let's see the first part. The first part is to measure the resistance per unit length of the wire of a meter bridge. Well, that's quite simple, and you can see that I have denoted resistance per unit length as lambda. In some books you might find that they use rho, but I like to save rho for resistivity, because you know resistivity is resistance per unit length times the area of cross section, so it's not really resistance per unit length. So I'll not use rho here, I'll use lambda here. This is the first part, and the second part is to determine an unknown fixed resistance by Carey-Foster method. Well, both the parts are using Carey-Foster method, so that's how we'll proceed. We'll first find out lambda, and then we'll try to find out an unknown resistance using lambda. We'll see what's happening here. It's not that tough to follow. One thing is very simple. You have already guessed that to find any unknown fixed resistance, the method we apply is the Wheatstone bridge. Well, what's the Wheatstone bridge? That's very elementary. I have shown a diagram here, which is one of the most conventional diagrams around. There are four resistance arms. We'll call them ratio arms. The top left arm contains resistance P conventionally. The top right has Q, the bottom left has R, the bottom right has S, and the battery B is causing a current to flow through this circuit. There is a galvanometer G which is connected across the junction of PQ and RS, as you can see, and the battery is connected in the junction of PR and QS. Well, the current gets divided in the PR junction and again joins in the QS junction. I'm really not interested what happens outside this resistance arm loop. Let's see what happens inside this, and you have done this derivation a lot of times. But still, let me just do it for you. I have divided the current into two branches, I1 and I2. The I1 branch again gets subdivided into IG, that flows inside the galvanometer, and into I1 minus IG, that flows to the Q branch. And I2 joins with IG and then flows into resistance S as I2 plus IG, and again these two currents join and again they go back to the battery. So that's simple. Now I'll apply KVL to these two loops. When I apply the KVL to the first loop, this is the equation you get, and it's very elementary. What I have used as convention is as sign convention. I have taken the voltage drops along the current's way as negative. So it's minus I1P, minus I1G, and I2R as positive. In the first loop, this all sums up to 0, as we know from KVL, and the second loop will obviously give a voltage drop across Q, a voltage gain across S, and a voltage gain across G. So that will sum up to 0 again. And you know the next step, it's obvious. I will equate the galvanometer's current to 0 to find the balanced condition. Because as you know, when the bridge is balanced, the potential difference between the PQ junction and the RS junction is same, and so you know it's shorted, no current flows. So anyway, if I put Ig equal to 0, it's very obvious from the above two that you can see IgG term cuts off and this IGS term cuts off from equation 2. From equation 2, another term IgQ gets cut off and IgG also gets cut off. So as a whole, 4 terms got cut off. What are we left in equation 1? We are left with minus I1P and plus I2R. And in equation 2, we are left with minus I1Q and plus I2S. So it's quite simple to see that the condition for balance will be, as you all already know, it's P by Q equal to R by S. You have seen this derivation in a lot of ways, in many different ways, a lot of times. So it's not really very important for me to spend too much time here. I just gave this as an introduction because this is what Carey-Foster bridge is based upon. So please remember Wheatstone bridge. We will move on to the next topic, which is the application of Wheatstone bridge, which you have already learned in college, in school rather. In high school, you have been doing electrical practicals, and to measure unknown resistance or unknown resistance or a resistance per unit length of the meter bridge wire, you have already used this thing called meter bridge. Well, a meter bridge is nothing but a 1 meter long wire which helps in forming the RS branch of the Wheatstone bridge. And between the two gaps that you can see in the left and right, we can connect the P and the Q resistances, which are fixed known resistances, or maybe Q is variable, or whatever. It's whatever the practical demands. We've already done this practical, so I'm not getting into details of it. What is very important, I want to note it here, is that the wire is really something that you must know what it is made up of. Why did I take up this point to be important? Well, the point is that you see, many things that we do in practical, we do not think why this is used, why that is used, or how to troubleshoot this. And if we are completely aware of everything that we are using in an experiment, we will be able to handle it, we will be able to control it, instead of it controlling us, which happens a lot of times that we don't know what's happening. Anyway, so that is what we try to teach at DPL, you know. This wire, many of you already know actually, is actually made up of manganese or constantan, and sometimes it's usually manganese. Okay, what's manganese? It's an alloy of manganese, nickel and copper, obviously, with copper as 84%, manganese had some 12% and nickel as some 4%. It's something like that. You can find it out in Wikipedia. What's important is that this alloy wasn't always known to mankind. You can obviously guess somebody made it, and the person who made this had something in mind. What did they have there in mind? It's very simple. They wanted to make a wire that has certain properties that will help us in balancing a Wheatstone bridge, right? So definitely he was looking for something. What are the properties that he was looking for? We can guess. Let's see. Firstly, this point is very important. Resistivity had to be a bit in the high range, but not too high. It should not be an insulator, of course, but it cannot be a conductor, because if it's a very good conductor like copper, then the current would just pass through it and it won't provide much resistance in a meter. It would provide, say, micro ohms in a meter if it's copper actually. Okay, do you get my point? So you cannot use it for a balancing practical because it won't provide any resistance at all. It will be almost a conductor. So we need a material which has moderate resistivity. Copper has resistivity, or rather most conductors has resistivity in the order of nano-ohms per centimeter. Well, this alloy, manganese, has something around 10 to the minus 4 ohm centimeter, which you can see is much more higher than copper. And obviously it's not an insulator, it's quite conductive. Then what is the next very important point, and this point actually made manganese the most indispensable alloy for this type of practicals. It was discovered in 1887, let me tell you, and it has been, you can see, 133 years maybe it's being used, and you can obviously see that this has to have some important property, and it is this: it has virtually zero temperature coefficient of resistivity. What is temperature coefficient of resistivity? It's very simple. If you remember from your school knowledge, that resistivity of conductors are said to be linearly increasing with temperature. How? Well, you know, it's rho equal to rho 0 bracket 1 plus alpha T0, where rho 0 is any temperature, resistivity at any temperature, which is T0, and with increasing temperature, the alpha, which is temperature coefficient of resistivity, which is a constant, will add a term to resistivity. So rho at any temperature is equal to rho 0 1 plus alpha into that temperature. Well, the point I am making here is, if the alpha is quite high, then what happens is, as temperature increases, the resistivity of a material changes, actually increases, as you already know. So I will need a material here for which the resistivity will remain constant for a long range of temperature, because you see, this is a practical of electricity, and due to Joule's heating, there is always heating going on as the current flows, and with this heating, if the temperature of the material rises and in turn it goes on to rise the resistivity, well, that will be a problem, because my null point will shift, as you can already guess. So I need a material which has very low temperature coefficient of resistivity, and let me tell you, for manganese it is really 0 at 25 degrees Celsius, which is room temperature. At other temperatures it is of the order of -5 per Kelvin, which you can see is very negligibly low. So manganese was a great discovery. It really stayed for 130 years, and I guess it will stay for much longer also. What are the other properties it must have? Well, this is another property that it has, that it has very low linear thermal expansion coefficient. That is, with heat, you already know that the material expands. So with heat, if it expands, of course my null point will again shift perhaps, so that is not allowed, and this material has it in the order of -6, which is very low. And lastly, it has exceptionally high modulus of elasticity. Why is it important? Well, there may be many types of stress forming inside. In fact, due to heat, if it even increases a bit, after switching it off, it needs to get back to its original position. So if elasticity is very high, it will instantly get back to its unstretched position, even if it expands a bit, right? So the point is, the high modulus of elasticity helps it in coming back to its original position as soon as the stress is released. Well, another is very important point here is that if you are willing to play guitar with the bridge, well, it won't affect much, because it has a high modulus of elasticity. Even if you scold you, it's not a problem, because it will come back to its position very soon. But please don't play. So you can see that this is a very important development. So we must know the person who developed this. He actually made Constantan first, and then he bettered that by manganese. And you can see that he was not really much known to the world for this discovery, which he should have, because this is a great discovery. You have no idea how much it helps us in every place where we need these properties. So let's see the name of the person. Well, there it goes. You have heard his name already, because you have already heard that the galvanometers that you use, which we call table galvanometer, is actually called Weston's galvanometer, and that was developed by this man. Can you see how big he I mean anyway, I got excited there. So you can see that using this method, when you have a resistance in the top left P, a resistance in top right Q, using the Whitson bridge formula for null condition, you can have P by Q equal to L1 by 100 minus L1, which is obviously measured from any side, left or right. Here I would prefer left side, just as convention. So whenever I say any length, remember that I am talking from 0 at the left to that length. Okay. One thing to note here is that R by S got changed to L1 by 100 minus L1 simply because I considered that R, which is the left side of the null point is equal to rho L by A, where L is L1 and rho is the resistivity of this meter wire and A is the area of cross section of this meter wire. And again in the denominator we had S, and I changed it into rho into length by area, where again this is the same rho, this is the same area, but the length is 100 minus L1. So you can see rho and area gets cancelled, so you're left with this. But a very important point to note here is this is an approximation, because practically it's not really very uniform, so the area of cross section changes and the resistivity might not be exactly constant throughout. But anyway, apart from all this, let's think that it is quite constant because they are made with much precision. Actually these meter bridges really cost a lot, so basically I can think that they are made with much precision. So this is the formula. Please remember this formula, we'll need this later. So we can move on to the next slide. Oh, hold on, what? There's a problem with this method? Well, you never had a problem when you did it in school. Let me see. What can the problem be? Okay, the problem can be of many types. It might not be accurate, right? Or maybe it might not be repeatable. There are a lot of problems when you design an experiment. Let's see what the problem with this practical might be. Well, suppose you have a resistance, say P equal to 1 ohm and Q is unknown. Well, say you cheated and you measured it, and the multimeter, which is very precise, which is a milliohm meter, showed 970.8 milliohm, which was supposed to be 1 ohm maybe, because that's how the designer designed it. And suppose the P you measured with the same multimeter and it shows 1 ohm. It's like that 1 ohm is made from a good shop, that Q1 is not. Anyway, but it's unknown to you, remember that. Now when we are solving for the length, we can theoretically do that because we have the formula up above in equation 4. You can have your own calculator. I'm giving you time. You can just solve this and you can see that you will get L1 equal to 50.74 centimeter. There will be a repeating decimal after that. I have left it out because I had only 4 significance figures in the above 970.8. Anyway, so let's move on to the problem. What's the problem? Yeah, this was theoretically operant, right? Because you knew the value of Q, right? But in reality you don't know the value of Q. When you're doing the practical, you just know P. So what you're going to do is you're going to put P in top left, put Q in top right, and then you are going to connect a battery, a galvanometer, and just like a Whitsun bridge. I guess you can imagine the picture in your head, right? You'll be touching the jockey and then you'll be finding the null point where the galvanometer will show no deflection. Well, will you be ever be able to get 50.74 centimeter? Unfortunately no, because the meter scale will have marking only for at least half a millimeter. I am sorry. Oh yeah, I'm right, it's 0.5 millimeter. So you can get at most up to 50 centimeter, which is again divided into millimeters, so 50.7 centimeter. But then you can only have 50.75, 50.70, 50.80. You will not be able to get 50.74, right? And if you are unfortunate, you might just have 50.7, 50.8. In most meter scales, they don't even have that half millimeter mark. You just have those 1 millimeter marks, right? So let me just think that I have a meter scale which has 50.7 and then it has 50.8. So while getting this null point, it will come slightly towards left in 50.7 and slightly towards right in 50.8. It will try to get a null point between 50.7 and 15.8, but you will not be able to measure the value because the scale does not have the reading. So you might want to take 50.7 as the null point, right? So although we never do a practical just once, we do it statistically many times and etc. But let's just forget this. Let's just say you get the null point as 50.7, you record this, and then after calculation you find out Q using the formula in equation 4. You can do it right now. I am giving you time. You can find the value will come out to be 972.4 milliohm, which is not quite what it was. You will argue that well, this is just in the order of 1 milliohm, so is that much significant? See, it's not really significant what you are really bothered about. The point is, when you're a say you're a shop owner, say you're a say you make resistances, okay? So suppose you make 1 ohm resistances, just like the guy you bought from, right? And suppose he does not make it 1 ohm, he makes it point with some error like this. He made it 0.98, right? How did he make it? Very simple. He put a known 1 ohm on the left side and the new wire on the right side, and then he kept on cutting the wire as long till the null point comes to 50. Okay, you can get it. So at some point the null point will come to 50 and he will say this much length of the wire is 1 ohm. But if he uses this method, there is a chance that for a small amount of values of resistances, the null point will remain at 50, because this is not very precise, right? And that is the problem with this method. If that person makes another resistance using this new resistance, again he might introduce an error, and slowly it might accumulate, and obviously you can see this method is not a very good method to calibrate resistances. Because of the small error also, we cannot use this for very accurate measurements, and you will agree with me now that this accuracy is very important. So this method actually lacks accuracy and precision. Well, there's a catch here. Accuracy and precision are written in the same sentence. They do not mean the same thing. I'll not go into much detail about this. I can just say this much, that accuracy is how much the data that you obtain is near to the actual known standard value. And precision is like, if you've taken the data many times, if the data is every time coming nearly same as the standard value, then we say that your measurement is precise. So precision has to do something with repeatability, and accuracy has something to do with how much close your data is to the real data. So let's say that this method does not have accuracy. And why does it not have precision? Because of the example I just gave you. Anyway, so what can we do? We need to increase accuracy. So we can actually think of something. Let's see. Well, one attempt at increasing the accuracy can be increasing the total length of the wire. That is, if the length of the wire were not 100 centimeter, but instead it was 1000 centimeter. Then from the previous example, we can obviously think that the null point won't be obtained at 50.74 theoretically, but 507.4 centimeter. Do you get it? So if I had a much larger wire, the null point would not fall at 50.74 but at 507.4, and that can be measured because I'll have that 0.4 in the millimeter scale. I hope you understood the point. And you have already seen such a thing. You have seen a potentiometer, right? Which is already there. You're seeing it. There's a problem with this. Well, you will say again problem. Yeah, there is, because you see that although this might seem a very good solution to the problem, and if we need one more decimal place, we can again increase the length of the wire 10 times, say 10,000 centimeter, and we can get up to the next decimal place. Well, this is a very good method, it seems to you. First problem you have already identified is how much longer will we make it to measure up to a greater precision. It's not possible, right? But even farther than that, there is another problem. The problem is that every time you are turning around the corner, you are having more contacts, and with every contact you are having more stray resistances, which are called parasitic resistances. I won't get into details of that. I'll talk about those things later in class maybe. And also it introduces, due to these contacts, some thermoelectric effects like Seebeck and Peltier effects. Well, again, I'll not go into details of all those, but the point is it's problematic. So it's, again, as you increase the number of turns, that is, as you increase the length, it will have less and less precision and accuracy. So it's not a great solution either. So what's the solution? We'll see in the next part. Thank you for listening to me. Please follow me in the next part.